as can be checked from the schedule for this ATAL FDP, we have two back-to-back. Means in the previous day, that is in day 2, session 4 was already taken by Dr. Vaidya Shankar. So I think we don't need to go for brief introduction about the sir. Rather, I would like to ask sir to start his today's session. Sir, over to you.
Thank you, sir. Thank you so much. Am I audible, sir?
Yes, sir.
Okay, okay, we'll start. So I tried to share my screen. I hope my screen is visible to you.
Yes, sir, it's visible.
Yes, ma'am. So this is IBM Qiskit IDE. IDE stands for Integrated Development Environment. So people from non-computer science and IT, they don't know about this. So this platform is IBM Qiskit IDE. Okay. So yesterday we discussed about the acronym for Qiskit. Qiskit stands for Quantum Information Science. Quantum Information Science. Information Science. Toolkit. So this is the acronym for Qiskit. Okay. So what is the acronym for IDE? Integrated.
नहीं बेटा ऑन कर रही हूँ अभी ऑन हुआ है
Development Environment. Okay. So what it means, within the same environment, you are able to create a quantum circuit. You are able to create a coding for that. You are able to run, execute, compile each and everything in a single platform. Okay, that is the meaning of integrated development environment. So no need to go for each and every tool. No need to go for each and every tool. So in last class, what we discussed? We discussed about empty circuit.
Sir, excuse me, sir.
Yes, sir. Yes, sir. Please tell me. Am I audible? Is my screen is visible to you?
Yes, sir. It is okay. All
okay.
You can go ahead.
Okay, okay, fine. So yesterday
Hello. Hello, sir. Hello. Sir, actually, we are not getting your sound.
Hello, am I audible? I'm the co-coordinator of this FDP. I think this session should be continued with Dr. Jaikumar Vaidya Shankar, and whenever we'll be finishing this session, we'll take all the questions from the audience. Meanwhile, please let sir to carry on to their session. Please stay with us. We are muting all the participants. Sir, please continue. We'll take the question at the end of this session. Please cooperate, audience. Sir, please continue.
in last class, what we covered about empty circuit, we covered about NOT gate, we covered about Hadamard gate. Okay. So in today's session, I tried to quickly revamp. So go to IBM Quantum Composer. So I'll share what it is supposed to search. So go to IBM Quantum Composer. So Google for this. Even if you don't have account also, you're able to do this. So please go to Google and search about IBM Quantum Composer. Okay. So if you go to Quantum Composer, the layout will look like this. So it will contain a musical note like dashed line. Okay, it contains 4 qubits, 4 classical bits. Okay, then it contains 4 quick output called phase disk. Then you can see probabilities. Then you can see Q sphere. Then you can see coding part. Okay, this is the integrated development environment. So what we're supposed to do? We're supposed to use only one quantum bit. So for that, so click Q0, keep only one quantum bit. So click C4, select minus button, keep only one classical bit. I hope this session is recorded. Sir, whether it is recorded, please check.
Yes, sir. Yes, sir.
Okay, fine.
We are recording all the sessions.
Okay, good. So what we do, we keep only one quantum bit. Only one quantum bit. Okay, which is called Q0. And we keep only one classical bit. Only one classical bit. Which is called C1. Okay. So you need to modify your circuit in such a way. So keep only Q0 and C1. And look at your output. So downside you can see computational basis. Suppose if it is not visible, I try to zoom. So downside you can see the probabilities window. Here you can see computational basis. For a single qubit, how many possibilities are there? Basis state, 2 states, either 0 or 1. Okay. So in same way, you can look at your Q sphere. Now your circuit is empty. So observe here, your circuit is empty. Circuit is empty means it is in state 0. It is in state 0. Okay. So how to represent state 0 in a Q sphere? It will point to North Pole. So extreme point of northern hemisphere. Okay. So this is the meaning of this circuit. Then what do you do? Go to view, go to panels, enable state vector. So you will have one more window which is called state vector. So the difference between state vector and probability, okay, state vector is purely related to signals. So what is the signal of state 0? So this blue color line. So this is the signal strength of state 0. And what is the signal strength? So if you move mouse over here, you can see amplitude equal to 1, which means full signal strength for stage 0. Okay. So look at the probability. What is the meaning of probability? So probability for stage 0 is now 100%. It means if you measure your quantum circuit, okay, if you try to measure your quantum circuit, which will give value 0. So in between I tried to close this magnifier. Now your circuit is starting with stage 0. You are preparing your qubit. Your quantum bit in stage 0. Okay. So that is why it is pointing to North Pole. So this is the signal strength of stage 0. So where it will point? Over here. Okay. So if you take modulus, if you do square, you will get probability. If you take modulus, if you do square, you will get probability. Okay. So what is the amplitude of stage 0? 1. So taking 1 as the amplitude, and if you are doing modulus, if you are taking square, you will get 100% probability. So this is what it means. Okay. So try to create your circuit in IBM Quantum Composer. So check your chat box. I shared link over here. So Google IBM Quantum Composer. If it is possible, try to create a login. If it is not possible, just work without login. So no issue. I hope everyone able to follow. Move your mouse over the probability. Now we can see probability equal to 100%. Where it is pointing? In stage 0. Okay. So this is the measurement gate. This is the measurement gate. I try to zoom. So this is the measurement gate. Measurement gate. Okay. So what this measurement gate will do, it will convert quantum information into classical information. So what is the form of classical? It is the form of binary. Exactly, if you want to mention, it is in the form of bit. Okay. So what is the form of quantum information? Quantum state. So this will happen. So once you do measurement for any quantum bit, your superposition state will get collapse. So this is one more point. Once you do measurement to a quantum bit, superposition will get collapse. So all your quantum information will turn into classical information. So this will happen. So you need to be very careful when you apply any measurement. So imagine quantum information qubit like a soap bubble. Okay. So once you try to touch that soap bubble, what will happen? Soap bubble will burst away. So you cannot recreate the same soap bubble after you measurement. If you do measurement or touch that soap bubble, same thing will happen. Okay. So once quantum information is lost, it is lost forever. So information will last forever. So this is interesting phenomena about quantum. Okay. So what we did, we started qubit with stage 0. We tried to measure that qubit. Okay. What happened? You will get 100% probability of binary value 0. So your quantum state is converted into binary value. Fine. So try to observe carefully. I click this measurement gate. I try to press delete button so that you can remove that gate. Otherwise, you can click this gate and you can select bin button. So multiple way to remove this measurement gate. Okay. So recall the previous experiment. What we did, we tried to focus on NOT gate. So we prepared qubit with stage 0 by default. So this is by default in IBM. Okay. Then we applied a NOT gate. So what NOT gate will do, it will change from stage 0 to state 1. So power supply will happen. We represent the state in the form of state 1. So some changes will happen, right? If you apply NOT gate from 0 to 1 or 1 to 0. Okay. So that is why the state is changed from state to 1. Now you can see the output variation over here. Output variation. If you move your mouse over here, you can see probability of state 1 is 100%. Now look what are all the changes happened in your key sphere. Now it is pointing to South Pole. South Pole. So which represents state 1. Okay. So look at the changes over here. Now you got full signal strength for state 1. So this is full signal strength. Because your signal is pointing towards South Pole. Okay, towards South Pole. And look at the probability. If you try to measure this gate, what happens? So try to do measurement of your Q0. Try to do measurement of your Q0. Now, you need to do this formula. So apply modulus to state vector and do square, and you will get probability value, which is 100%. So what is the signal strength of 1, which is yielding your probability to get binary value 1 with 100%. So this is binary value 1 with 100% probability. Okay, so this is state 1. So here you can see state 1. State 1 is quantum state. But when you do measurement, quantum state will convert it into binary value. So remember this point. Okay. Now try to delete this gate. Now try to delete this gate. Now what we do? We try to implement Y gate. We try to implement Y gate. So here you can see Y gate. So if you have laptop, if you have CPU, so try to follow this. So you can see Y gate over here in maroon color. So try to plug Y gate over here. And before that, we can see what is the operation of Y gate. Okay. So I'll share this link with you. So look at your chat box. So meanwhile, if you have question, please keep it in your note. So you can ask after that. So go to this link. Go to this link. All of you able to land in this web page? I hope so. Okay. So these two are pure states. So state 0 and state 1 are called pure states. It is not moving. Okay, I will choose both. Okay. So these two are pure states. So imagine state 0, state 1 are called pure states. Okay. What we covered yesterday, we covered X gate, then we covered Hadamard gate. So we covered 2 gates. Now we're going to discuss about Y gate. We're going to discuss about Y gate. So now you are in stage 0. Stage 0, it is pointing to North Pole. So click Y gate. So every one of you click Y gate. Or note down what I am doing. So if we are not able to do parallelly, note down what I am doing. Now we are in state 0. Then we applied Y gate. So what happened? It will go to state 1. So this is exactly like X gate. So which will do bit flip. Which will do bit flip. But if you look carefully, it will introduce pi by 2 phase shift. So this Y gate will do bit flip along with pi by 2 phase flip. So y gate is somewhat greater than x gate, somewhat greater than x gate. Okay, so both will do bit flip, both will do bit flip, but y gate have additional capacity, y gate have additional capacity, it will do phase flip, it will do phase flip. So remember these terms, remember these terms, and you can see phase flip only downside, and you can see phase flip only downside, right? So we try to compare one more time, we try to compare one more time. So click y gate in state 1, it will go back to stage 0. Okay, so initially we are in stage 0, we applied y gate, it will go to state 1 along with pi by 2 phase flip. Okay, again if we are applying state y for this, it will go back to stage 0. So which is like if we apply 2 y gate next to next, which will cancel each other, which will cancel each other. Okay, so it means y gate has its own inverse, has its own inverse. So if we apply twice, which will cancel each other, which will go back to original state, which will go back to original state. So if you understand this, let's do one more time. So click stage 0, click X gate, you can see bit flip, but there is no phase flip. From state 1, if you apply X gate, it will go back to stage 0. Okay, now you can select Y gate. From stage 0, apply Y gate, it will do bit flip along with phase flip. Again from state 1, if you apply Y gate, it will go back to stage 0. So same way, you can check with Z gate. So click Z gate in stage 0, it will do nothing. So next gate, we try to cover stage 0, then we try to apply Z gate. So what happens? Nothing will change. So state retained, state is retained, nothing will happen. Okay, so apply Z gate in state 1, what will happen? So try in your tool and tell me the answer. Try your tool and tell me the answer. From state 1, if you apply Z gate, what will happen? Apply Z gate. Apply Z gate.
The pi value changes.
Yes, ma'am. Exactly. The pi value will get changed. So click state 1. Click state 1. Apply Z gate. It will introduce phase value about pi rotations. So Z gate will introduce pi rotations in phase in over all points in block sphere, over all points in block sphere except stage 0. So note down this point. So Z gate will introduce pi rotation. So what is the meaning of pi rotation? Negative sign, or you can say sign change. So look at here, stage 0 reside at positive side, positive plus. Okay, pi reside at negative side, so this is negative state. So which means opposite side of your sphere, opposite side of your sphere. So when you are dealing with Z gate, it will introduce phase change in your phase. because it will happen over pi rotations. That is why it will go for opposite side. Okay. So you can write like in this way, state 1, if you apply Z gate, it will turn into minus state 1. So if you apply Z gate for minus state 1, it will go back to state 1. So this is the logic. So what you do? So click Z gate in minus state, minus 1 state. So it is in pi. Okay, click Z again, it will go back to state pi 0. So again click Z, it will go to negative side. Again click Z, it will come to positive side. Okay. Then click 0, click 0. Okay. Click Hadamard gate. Now what we did? We are in stage 0. Now we applied Hadamard gate. It will go to positive state, which is very special state, which is called equal superposition. Equal superposition. Okay. Now what you do? Click Hadamard gate in positive state. Click Hadamard gate in positive state, which will go back to stage 0. Now apply Hadamard gate in positive state, which will go back to stage 0, original state. It means if you apply two Hadamards next to next, it will cancel each other. It will cancel each other. So it means X gate, Y gate, Z gate, Hadamard gate have its own inverse. Have its own inverse. If you apply twice, the effect is get cancelled. That is the meaning of these 4 gates. Okay. So we try to create all these gates in our Qiskit composer. Okay. So for an example, we already covered about X gate. Once again we can recall. Okay. Now in stage 0. If you apply X gate, what happens? If you apply X gate, which is NOT gate, it will turn into state 1. So everybody know how it is happening, right? Apply one more time NOT gate, which will cancel each other. Apply one more time NOT gate, which will cancel each other. So state 0, NOT gate 1, turn into state 1. Again apply NOT gate, which will turn into state 0. So two NOT gate next to next will cancel each other, because X gate has its own inverse. Now recall the previous notes what we covered. Okay, apply Y gate in stage 0. Apply Y gate in stage 0. So what Y gate will do? So we start from stage 0. Y gate is NOT gate plus pi by 2 rotations in phase. So that is why you will get state 1. But additionally, the pi by 2 phase shift will happen. So you can see this color change over here. You can see color change. Okay. So one more time, if I apply Y gate, what happens? Two Y gate will cancel each other. Okay, both of their effects. So Y gate have its own enemy. Inverse is own enemy, right? Equal to each other. So I hope you are able to understand X gate and Y gate. Okay, so delete one Y gate. You can see the difference in phase. Next, try to apply Z gate in stage 0. Now we covered stage 0. Okay, we applied Z gate. What Z gate will do? It will introduce pi rotations. in phase, which is nothing but sign change. Sign change. Okay. So what happens if you apply Z gate in stage 0? Nothing will happen. So nothing will happen. So this circuit is somewhat special. So nothing will happen. Nothing will happen. If you apply Z gate in stage 0, it will remain in the same state. Okay. So delete this Z gate. Delete this Z gate. What do you do? Try to implement a NOT gate. Try to implement a NOT gate followed by Z gate. Now you see the phase change. So what is the phase change? So stage 0, we apply NOT gate. Okay. Then it will turn into state 1. Then we again apply Z gate. It will change sign. After this, you will get minus state 1. So this minus is depicted in this color. So you can see this color over here. So I will zoom for your convenience. Are you able to see the pi value which is in red color? So that is why your output got red color. With the help of color code, you are able to see whether any phase change happened in your circuit or not, quantum circuit or not. Okay. So apply Z gate over here. What happens? So both Z gate will cancel each other. It will nullify phase rotations. So you'll get normal NOT gate operation. So you can see phase angle equal to 0. So delete one NOT gate. Again, you're supposed to implement phase change. So phase angle equal to pi. Everybody able to follow? Okay. Now what I do? I try to implement Hadamard gate. I try to implement Hadamard gate. So what Hadamard gate will do? If you introduce 0, if you introduce your qubit in stage 0, if you apply Hadamard gate, which will create equal superposition. Equal superposition. Okay. Normally, if you apply stage 0, if you apply Hadamard, it will go to positive state. So positive state lies in equator. That is why you will give half circle for stage 0, half circle fill for state 1. Now look at the Q sphere, equal superposition. At the same time, it is able to point both North Pole and South Pole. Okay. Then look at your state vector. So what is the value of state vector? What is the value of state vector? Move your mouse over here. I'll zoom for your convenience. Move your mouse over here. It will show 0.707 for stage 0. So amplitude of state 0 is 0.707. So move your mouse to state 1. It will give 0.707. So which is nothing but 1 over root 2. 1 over root 2. So this is 1 over root 2. Okay. So if you want to get amplitude, if you want to calculate probability out of your amplitude, what you're supposed to do? You need to take modulus, then you need to do square. So converting from state vector amplitude into probability, you need to do modulus and you need to do square. If you do so, you will get 0.5. 0.5. In terms of percentage, you will get 50% of chance for 1, 50% chance for 0. So I will delete this ink mark. Now you can see the probability. So move your mouse over here and you can see probability of state 1 is 50%. Probability of state 0 is 50%. Okay. So after Hadamard, what you will do? Try to do measurement. After Hadamard, what you do? Try to do measurement. So if you measure, what happens? If you measure, what happens? The equal superposition is collapsed. If you measure any qubit, so forget about equal superposition. If you measure any qubit, maybe I'll rewrite. If you measure any qubit, superposition will get collapse. What is the literal meaning of this? Your quantum information, your quantum state or information will turn into classical forever. Classical in terms of bit. It is in the terms of qubit. So this will happen forever. So you lost your quantum information forever. So this is the final process we need to do. Measurement always happen finally. So you should be very careful when you do measurement operation. So it is like trying to touch a soap bubble. Imagine your superposition is just like soap bubble. Okay. So what is the quantum state you will get after Hadamard? Positive state. So positive state because you are starting from 0. From 0, if you apply Hadamard gate, you'll get equal superposition, but where it will go? It will go to positive state. From positive state, again, if we are applying Hadamard, it will go back to stage 0. Okay. Now check whether it will happen or not. If you apply 2 Hadamard gate, which will cancel each other, you'll get value 0. You'll get value 0. Now delete this measurement gate. Again, you can see the superposition. Okay. So delete this Hadamard gate. Now come to the block sphere. So we covered X gate, Y gate, Z gate, Hadamard gate. Next, we're going to see about S gate. Okay. So to implement S gate, you need to start from some superposition. Okay. So these 4 gates are Pauli gates. These gates are Pauli gates. So I try to mute all. Okay, no issue. So X, Y, Z are called Pauli gate, and Hadamard gate will create superposition. S, S dagger, T, T dagger, all these gates are why it is not coming? Yes, S dagger, T, T dagger are called. My tool is not working. So wait a minute. Okay, better I'll use open board. Yes. So X, Y, Z are called Pauli gates. Pauli gates. Okay. So yes, S dagger, T dagger are called phase gates. Phase gates. Okay. Now what we did? From stage 0, we applied Hadamard. it will go to positive state. From positive state, if we try to implement S gate, it will go to y-axis. So from positive state, if we apply S gate, it will go to y-axis. So what is the other name of y-axis? Positive I gate. Positive I gate. Okay. So x-axis stands for real axis. Real axis. Y-axis stands for imaginary axis. So all your imaginary component will exist in y-axis. So this is the idea of x and y. Okay. Now apply S gate in state S. Apply S gate in state S. So which means from I, if you apply S gate one more time, it will go back to minus state. So it will lead to minus state. So look at the flow. From 0 we started. I'll use pointer. From 0 we started. We applied Hadamard. It will come to positive state. From positive, if we apply S gate, it will go to y-axis, I state. Okay. From I state, if we apply S gate one more time, it will introduce pi by 2 phase rotation in xy plane. So S gate will introduce pi by 2 phase rotation in xy plane along with z axis. So imagine this is the z axis. Okay. So this will rotate in this way. So it will introduce pi by 2 rotations. So this is the meaning of S gate. So applying 2 S gate will not cancel each other. Apply 2 S gate will not cancel each other. So it is not like all these 4 gates. So S gate don't have inverse. S gate don't have inverse. Okay. So for that, what we supposed to do? We need to create a new gate which is called S dagger. So this is called S. This symbol is called dagger. So this is opposite of S gate. So it will introduce pi by 2 phase rotation in clockwise, where S dagger will introduce in anti-clockwise. So this is the minor difference between S gate and S dagger. It will introduce in clockwise rotation in phase. This will do in anti-clockwise. Okay. So one more time I will cover what is the meaning of S gate and S dagger. So click stage 0. So we try to follow stage 0. From stage 0, if we apply S gate, I'll change gate color. S gate, which will lead to sorry. So from stage 0, S gate will not work. So for that, what we supposed to use? We supposed to use Hadamard gate. So apply Hadamard gate from stage 0. So check over here. So click stage 0, apply Hadamard. It will come to positive state. It will come to positive state. From positive state, if you apply S gate, what happens? From positive state, if you apply S gate, what happens? It will go to plus I state. Will go to plus I state. So check over here. So now it is in positive. From positive, if we apply S gate, it will go to plus I, y-axis. Okay. From plus I, if you apply one more time S gate, where it will go? It will go to negative state. It will go to negative state. Okay, to reverse this process, what we supposed to do, we need to apply S dagger. So here I try to change color. So if you apply S dagger, it will go back to original state. So what is the previous state? Plus I. So one more time, if you are applying S dagger over here, what happens? It will go to positive state. So click S dagger and observe what happens. It will go to positive state. I hope everybody able to follow. Everybody able to follow. So any doubt until now? Put in chat box. Stage 0 and phase of pi. Whether it is answer, okay, follow. Okay, fine. So click stage 0. Click stage 0. Apply Hadamard gate. So I will write down the sequence. So we start from stage 0. Then we applied Hadamard gate. It will go to positive state. It will go to positive state. From positive state, if you are implementing T gate, so this is new gate. So observe where it will go. It will go in between positive state and plus I state. So this will go in between positive state and plus I state, which means it will introduce pi by 4 phase rotation. It will go pi by 4 phase rotation in XY plane. In XY plane along with Z axis. Sorry, XY plane. So click one more time T gate, it will go to state plus I. State plus I. So you can observe 2 T gate equal to 1 S gate. Okay. So if you apply T gate from positive, it will go to plus I state. Okay. If you want to do the same thing, if you want to do the same thing with the help of T gate, so T gate, if you apply plus, it will go to in between. It will go to in between plus and plus I. Okay. If you apply one more T gate, it will go to plus I. Sorry if you got little confused. So what is the point? Normally, if you apply 2 T gate, it will equal to 1 S gate. Okay, remember this formula. Now what we do? Try to click stage 0. Try to click stage 0. Okay. Apply Hadamard gate. Apply T gate. Apply T dagger. So T dagger is opposite for T gate. So T dagger is opposite for T gate and S gate is opposite for S dagger. So all these gates have own inverse. Own inverse. So these gates don't have own inverse. That is why we created opposite gate. So this is the logic of all these gates. Okay. So if you understand all these gates, try to work on. Click stage 0. Click stage 0. Apply Hadamard gate. Apply Hadamard gate. I will note down this state. So click stage 0. Next, apply Hadamard gate. It will lead to positive state. It will lead to positive state. From positive state, if you apply Z gate, what happens? If you apply Z gate, what happens? It will go to state minus. So check over here. Now it is in positive state. Apply Z gate. It will go to state minus. So Z gate will introduce pi phase rotation. So if you took notes beforehand, so you can see Z gate will introduce pi phase rotation. So are you able to compare Z gate, S gate, T gate? So 1 Z gate equal to 2 S gate equal to 4 T gate. So note down this formula. 1 Z gate equal to 2 S gate. Otherwise you can remove this one. So it will have meaning. So Z gate equal to 2 S gate equal to 4 T gate. So by deriving formula like this, by comparing gates like this, you can able to reduce gates in your circuit. So that is the whole logic. Okay. Now what we do? We try to implement all these gates in our circuit. We are about to check whether it is working or not. Any doubt? Yes. So which one, sir? Narayan, sir, which one I need to repeat? Are you able to follow? Okay, Hadamat gate. Fine. Okay. So click stage 0. Click stage 0. Click stage 0. Apply Hadamat gate. What happens? It will go to positive state. It will go to positive state. So go to this link and try by yourself. So that is why I shared this link. So if you joined late, please go to this link. Okay, click stage 0. Click Hadamat gate. It will lead to positive state. From positive state, if you apply Z gate, it will go to negative state. From positive state, if you click Z gate, it will go to negative state. It will go to negative state. So if you understand this, then what we'll do? We try to do a different gate combination. So click stage 0, click stage 0, click state 1. Now apply Hadamat gate, it will go to negative state. Now we are starting from state 1. From state 1, if you apply Hadamat gate, it will go back to negative state. From negative state, if you apply Hadamat, it will go back to state 1. Okay. In same way, from stage 0, if we apply Hadamat, what happens? It will go to positive state. From positive state, if we apply Hadamat, it will go back to stage 0. So both are in equator, right? Positive and negative are both are in equator. Both are equal superposition. Even plus I and minus I are in equal superposition. So whatever the point lies in your equator is exactly in equal superposition. Are you able to get this logic? Okay, we covered all these gates. And check whether it is working or not. So click composer. So this is new circuit. Sorry, this is the circuit we already covered. So here what we'll do? I try to close this. So try to put Hadamat gate. try to put Hadamard gate, which will create equal superposition. So now it is in positive state. From positive, if we apply S gate, what happens? It will introduce pi by 2 phase rotation. Now it will go to plus I state. Okay. So what is the color of plus I? This pink color. This pink color. So look over here, pi by 2. So this is how you are able to know where it is going. Okay. Apply T gate. What happens? T gate will introduce pi by 4 rotation. Now you can see darker shade of that color. Now you can see darker shade. Now it is in pi by 4 here. Okay. So one more time, if you apply pi by 4, what happens? One more time, if you apply pi by 4, it will introduce pi by 2 phase rotation. Okay. So how you supposed to calculate? How you supposed to calculate? So we started from stage 0. We applied Hadamard. Now it is in positive state. Okay. If you apply S gate, it will introduce pi by 2 rotation. Okay. So T gate will introduce pi by 4. T gate will introduce pi by 4. Now add all your phase gate, pi by 2 plus pi by 4 plus pi by 4. So which is equal to pi phase rotation. Which is equal to pi phase rotation. Now you can see the color over here, which is in red color. Okay, which is in red color. So which is the angle pi. Okay, so what I will do, instead of using 3 gates, I try to follow the formula. I delete 2 T gates. Instead of 2 T gates, I can apply 2 S gates. I will reach the same state. Now look at the angle over here, angle equal to pi. So I use the same formula. Instead of 2 S gate, I can apply 1 Z gate, which will introduce pi phase rotation. Again, you can see the same angle pi. So likewise, you can play with your gates. If you understand the basic gates in very strong manner, you are able to write a perfect quantum code. So most of the time we need to invest in quantum gates, how it is working. If you put one gate, what will happen in your circuit, where quantum state will change, whether the state will change from 0 to 1 or in between, or any phase shift will happen. So these many possibilities you can do if you play with your gates. Okay. Now what I will do, I try to delete all these gates. I try to create one more qubit. So click here, click add qubit. So click here, add one more classical bit. Yes, I will come for question. Yes, sir. Put in the chat box.
Can I ask, sir?
Yes, sir. Yes, sir. Please ask.
Now, with this help of what type of program I can write, sir?
Sir, if you want to create any program in computer science, we need to use AND gate, NOT gate, XOR gate. Same gate we are able to create with the help of quantum circuit.
Give one example. Try to suppose if you want to find the smallest number or greatest number.
Those
design?
kind of program we cannot do. Take an example of half adder. Take an example of half adder in Qiskit. So this is the circuit of half adder. I will cover these gates. So please wait for a while. I will cover these gates. Okay. So try to increase 1 qubit. Now we got 2 qubits, 2 classical bits. So it is a thumb rule. So how many quantum bits you have? How many quantum bits you have? You need to have equal number of classical bits. So it is a thumb rule. Okay. If you follow, it will be very good. Because when you do measurement, you need to keep all your equivalent quantum information in the form of classical value, binary value. So you cannot store quantum information anywhere, but you are able to convert quantum information into binary value. Okay, so this is out of this talk. So out of the syllabus, what I'll do, I try to drag before this. Yes, I try to do swap gate. So this is the swap gate. So this is swap gate. So what swap gate will do? It will take the value from Q1, it will redirect to Q0. Okay. In same way, it will get value of Q0, it will redirect to Q1. So this is the process of swap gate. Okay. We need to check this value because both are starting with stage 0. Both are starting with stage 0. That is why swapping not able to witness over here. So we need to check whether swapping actually happens or not. So we try to change one of these states. So what we'll do, we'll put a NOT gate over here. We'll put a NOT gate. Now both qubits starting with 0. So this is NOT gate. Now what happens? This will converted into state 1. So power supply will happen. So we redirect this power supply over here. Now your Q1 will get state 1. So what happens to your Q0? So Q1 value stage 0, that is redirected to, now I can mention in this way. So this will be better, right? Both starting with stage 0. So we swapped Q0 value to Q1 and Q1 value to Q0. That is why the outputs are interchanged. Now we can see this is stage 0 value. This is state 1 value. So how qubits are mapped in Qiskit? Q0 is mapped to rightmost bit. Q0 is mapped to rightmost bit. Okay. So same way, Q1 is mapped to leftmost bit. Leftmost bit. Q1. So that is why the output is 0, 1. Now we can see 1, 0. So you need to understand little reorder is needed in your Qiskit. So Q0 is mapped to rightmost bit. Q1 is mapped to leftmost bit. So the output is 0, 1. But if you want to see the base, it will be 1, 0. So this will sometimes confuse the beginner. Okay. So what happens if you try to drag and drop NOT gate in Q1? Now you can see changes in your output. So we started from 0, 0. Okay. Now it will become state 1. The state 1 is swapped to state 0, Q0. Okay. Oh, sorry about that. Sometimes. So state 0, I will use distinct color, state 0. So here it will change to state 1. The state 1 is swapped to Q0. So same way, this 0 is swapped to Q1. Now we can see the value over here. This is state 0 and this is state 1. So what is the combination? 0, 1. Okay, this is about swap gate. So select this swap gate, delete this, select this NOT gate, delete this. Next, we're going to cover about control NOT. So this is special gate, which is called control NOT gate. Control NOT gate. So in short form, they will say C NOT gate. C NOT gate. Okay. The first qubit will act like control. The second qubit will act like target. Okay. So imagine imagine your control is like switch. Your control is like switch. Okay. Your target is like equipment or device. Okay. The first control, the first qubit will act like switch. The second qubit will act like a device. Okay. So what is the value of Q0? State 0. What is the value of Q1? State 0. Okay. So it means there is no power supply. So it is in off state. It is in off state. So here what we did, we solved it, we tapped power supply from Q0 to this NOT gate. So there is no power supply over here. So if there is no power supply for this NOT gate become inactive. Inactive. So if there is no power supply, NOT operation will not happen. Okay. So it means the state will. So here also 0, here also 0. Okay. So to activate control NOT, we need to give control in Q0. So how to give control in Q0? By enabling a NOT gate. So stage 0, stage 0. So after this, it will turn into state 1. So which means power supply will happen throughout this wire. We soldered over here. So it will come down. So this will give power supply. This NOT gate is activated. Now it is switched on. So what happens if NOT gate is switched on? It will convert state 0 into state 1. So here also 1, here also 1. So remember, if you have NOT gate in Q0, power supply will enable. So here also you will get state 1, here also you will get state 1. Now delete this NOT gate. What happens? The Q0 is state 0, Q1 is also state 0. Okay. Now what we do? We try to implement Hadamard gate. We try to implement Hadamard gate followed by control NOT, which is equivalent to two possibilities. So first case, Hadamard gate could produce 0. Second case, Hadamard gate will produce 1. So it will have 50-50 chance. Okay, that is the meaning of equal superposition. Sometimes it will produce 0, sometimes it will produce 1. Imagine if it is producing 0, 0 means there is no power supply. There is no power supply. This NOT gate will not active. So stage 0 means down also stage 0. That is why you got 0, 0 over here. Now this possibility will happen if Hadamard gate produce 0. So this will lead to 0, 0 state. So what happens? So what happens if Hadamard gate produce 1? If Hadamard gate produce 1, so if Hadamard gate produce 1, power supply will happen. Power supply will happen. So this will come down. This will enable NOT gate. So here also 1, here also 1. So it will lead to 1, 1 state. It will lead to 1, 1 state. Now we can see these two gates are enabled. Sorry, these two states are enabled. So this is a special circuit which is called Bell state. Bell state. It is an example for entanglement. I hope in first lecture they covered entanglement. So what is the meaning of entanglement? If anything happened for one particle, the same effect you can see in another particle. Same effect you can observe in particle 2. Suppose this is electron 1, this is electron 2. So whatever happens for electron 1, the same kind of effect you can see observe in electron 2. So it have strong correlation. So this is not one directional, this is bidirectional. So whatever happens for P2 also affects in the same way of P1. So these two are like friends. So they always support each other. They always support each other. It is like a synchronized dance. So whatever happens for P1, the P2 also get the same effect. So Q0 is 0, Q1 is also 0. If Q0 is 1, Q1 is also 1. So what happens if you do measurement? What happens if you do measurement? Superposition state will get collapsed. You will get only one possibility. So 2 qubit means, if you have 2 qubit means, how many possibility you will have? 0, 0, 0, 1, 1, 0, 1, 1. But if you do measurement, so superposition state will get collapsed. Okay, you will get only one possible outcome. So what is the only one possible outcome? In this case, 0, 0. If you are running multiple times, you will get different outputs at each and every time. Okay, so only two possibilities, either 0, 0 or 1, 1 you will get. So in this case, we got 0, 0. So out of 4, how many possibility we are able to get? 0, 0. Sorry. So in this circuit, how many possibilities are there? 0, 0, 0, 1, 1, 0, 1, 1. So out of this, only these two are possible. These two are possible. Okay. So out of these two possibility, you'll get only one. You will get only one. So play with the circuit and be able to know what happens inside the circuit. So I delete this measurement gate. I delete this control node. Now what I do, I try to implement one more Hadamard gate. So this Hadamard gate will produce 0 or 1. And this Hadamard gate also produce either 0 or 1. Now we got 4 possibility. 0, 0, 0, 1, 1, 0, 1, 1. Now you can see all possible combination simultaneously. So 4 possible combination. Okay. So if you want to do superposition to collapse, what you do, you need to take measurement. So do measurement, what happens? Once superposition state is collapsed, you got only 2 possibility. So drag and drop this measurement to this gate. Now you got different possibility. So do measurement for both qubits, you got only one possibility. So are you able to follow this? Any question you can ask now? I will wait for question.
Whether these possibilities will change, sir?
Yes, sir, it will change. Each and every time, yes, each and every time if you measure, each and every time the output will vary. Because this is due to probabilistic.
No, whether we can run it now or when we can get it, sir?
Sir, you can run here itself. Simulation you can do. If you want to do real-time system, you need to select one of the system. Otherwise, you can use simulation. Okay, suppose if you want to do simulation, the best tool I will suggest, QBraid. So go to QBraid. Here you can do simulation. So how to run simulation you can get from IBM Qiskit website. Admit. So this will take one more session to define QBraid tool. Otherwise, you can use Google Colab. You can install Qiskit over here. You can use Jupyter Notebook. So many possibilities are there. So how to install Qiskit in Jupyter Notebook? If you search, it will come down. So these are simulation. So no need to work on the real system. By simulation, you can do. So use this command pip install QuizKit. You are able to use QuizKit in your GitHub, in your Google Lab. Yes, QML model will be built above with these gates. So these gates are fundamental. So if you want to work QML, first you need to thorough with these quantum gates. Minimum it will take nearly 6 months to understand these gates to create the better quantum circuit. Then you can go for quantum machine learning. So this is a simple gate for half adder. So I'll share this link if you are interested. So after this session, go and try. And what you can do, you can go for penny lane if you are interested in machine learning model, quantum machine learning model. So this is very good website. So people want to do quantum machine learning immediately, which is not possible. So you can do toy problem. So until it will take 10 to 15 years to do real-time problem solving. So don't try to compare classical quantum machine learning with the quantum machine learning. Okay, it will take some time. Then you can go for Google Quantum. Google Quantum, they have dedicated website. So each and every big company, corporate have quantum websites. Okay, interesting question. I try to answer that question. So I said quantum will do in probabilistic model. What it means, suppose if you have a problem 2 plus 2. Suppose if you have a problem 2 plus 2. So this is A, this is B. So input A equal to 2, B equal to 2 and operation is addition. Addition. Okay. If you write a code for this, if you write a code in Python or C or C++ or Java, okay. In classical computing, what you will get? Classical computing, if you are running for first time, what you will get? 4 as a result. Okay. If you are running for second time, what you will get? 4 as a result. If you are running for third time, what you will get? 4 as a result. If you are running for fourth time, what you will get? 4 as a result. So if you know your input, if you know your input, if you know your operation, okay, you can predict your output. You can predict your output. So this is deterministic in the way. So how many times if you are running with the same input, same operation, same code, you will get same output. But in quantum, if you have the same input, same operation, if you are running first time, you will get 4 as the output. Second time, you will get 3 as the output. Third time, you will get 2 as the output. Fourth time, you will get 1 as the output. So each time output varies. Why it is varying? Why it is varying? Because due to randomness. Because subatomic particle behave in very random fashion, random way. So each and every time you will get different output. Okay. So how to believe your quantum system if it is doing so? What you do? You need to run for multiple times. You need to run for multiple times. So how many times? Take an example of 100 times. If you are running for 100 times, now your output will differ. How it will differ? You will get 4 has 80% of the result, 3 has 10% of that result, 2 has 7% of that result, and 3 has 3% of your result. Now we are able to divide your correct answer with the wrong answer. So all these 4 are wrong answers. Okay, so this is correct one. So you need to run multiple times, then you need to do measurement. So I will mark it in red color. So do measurement after 100 times or multiple times. Then you'll know what is your correct answer exactly. So this is the quantum behaves. That is why you will get different output for same input and same output. So for addition, quantum is inefficient. So this problem is inefficient for quantum. Where in case if you want to do factorization which involved with permutation and combination, you can go for quantum. So whenever your problem involved with randomness, random guess, permutation, combination, you can go for quantum. Otherwise, classical is best. For addition problem, classical is best. So within a single run, you will get the output. I hope this will help you. So any more doubts?
Excuse me, sir.
Yes, sir. Tell me, sir.
Sir, we have 5 minutes left to end this session.
Okay.
Thank you,
So
sir.
any more doubts?
So please, so I think you can still continue for next 2 minutes.
Okay.
And after that, we'll be
fine.
taking few questions from the audience.
Okay.
Please continue, sir. Okay.
So here you can choose composer, or you can choose how many number of times you need to run your circuit. Okay. So normally they will give 2 quantum processor. So how many times you can able to execute? Only for 10 minutes. So per month, IBM will give 10 minutes time to execute your real quantum system. Okay. So after 1 minute, after 10 minutes, you need to pay 9,000 rupees per minute. So accessing quantum system is too costly. Okay. They gave 10 minutes for free access. Then you can see the changes in your code. I want to show this code. So this is about OpenQuasim. So I will zoom for your convenience. Now circuit is empty. Circuit is empty. So you can see view, panels, code editor. If you enable code editor, you will get this window. So here you can change Qiskit and OpenQuasim. So Qiskit stands for IBM Quantum Framework. Okay. So OpenQuasim stands for Open Quantum Assembly Language. Suppose if you are writing any code in Qiskit, if you want to run in Google system, then this will neutralize your code. So you can copy this code, you can paste in Google Quantum, it will convert according to that platform. Okay. Suppose if you want to use Microsoft Quantum System, this will help you. Okay. So go for Microsoft. Microsoft also having Microsoft Quantum. They have special language called Q#. So go to this website. I will share this link with you. You can run your quantum program using Qiskit. So go and search how to run in Qiskit. Okay. Go and search in Qiskit. So here you need to check your quantum processor. So if you click your circuit, if you click your system, if you click run circuit, it will run in your actual quantum system. So this is very simple nowadays. So initially you need to do all these parameter. Now they simplify this version. So I want to introduce one more tool called QSIM, which is developed by CDAC. So go to this link, QSIM. I will share this link with you. So it is a tool developed by Indian government, QSIM, quantum simulator. And also they have one more universe. So this is one more tool developed by CDAC. So please go and try this tool. If you know IBM Qiskit, both are so easy for you. So Qiskit will give a strong foundation in quantum. So try to register, ask permission for the usage. Okay, they will give access within 1 or 2 days. So this is exactly equivalent to Qiskit simulator. So this one on QSIM.
Hello, sir.
Yes, sir.
Am I audible?
Yes, sir.
We are almost at the end of this session.
Yes,
so can we, sir, take questions from the audience so that
yes,
we
sir,
can
we can.
address those?
We can take.
Yeah. Audience, anyone can raise your question?
Sir, in this
Is there any-
instance, what your type, sir?
What, ma'am?
This instance, what your type, sir?
You need to create an account. If you create an account, if you logged in, it will come.
Okay, sir. Thank you, sir.
That is why. Nowadays they are requiring a credit card to create an account. So make sure you cannot run your quantum circuit after 10 minutes. Otherwise you will get charged.
Okay, sir.
For safer side, what you can do, you can use QSIM and QUniverse, and you can install Qiskit in your simulator, Jupyter Notebook or Google Colab. That is more than
Okay,
enough for
sir.
understanding. Yes, ma'am. Thank you.
Okay. Thank you, sir.
Any
So-
questions from the audience side?
Sir, you said the factorization.
Yes, sir.
You explained about 2 plus 2. Can you explain about the factorization, sir?
Factorization, you try to search Shor algorithm, sir. I will mention Shor algorithm. This is the proven algorithm. This is the proven algorithm for factorization. So if you studied about digital signal processing, okay, quantum Fourier transform, they will apply all those idea over here. Shor's
With this, we are
support.
with this, we are at the end of this session. Thank you so much, sir, for your detailed description on your topic.
Yes,
So
sir. Thank you.
we
Thank
hope
you so
that
much.
yes, we hope that audience have enjoyed your session very much and that they have got 2 sessions. That means session 4 that we have conducted yesterday and session 5. Both were conducted by Vaidya Shankar sir. Thank you so much, sir.
Thank you,
With
sir.
this-
Thank you so much.
Yes, with this, we are ending this session. Audiences are requested to join to session 6, link of which already posted in WhatsApp. Please, you join to the next session, session 6. We are closing this session. Thank you.
Thank you, sir. Thank you.